Let's take a glimpse as to how SonarPoint can be deployed in various configurations to localize sound. So we are, you can use a SonarPoint recorder just to record sounds, but we will concentrate in this slideshow on how to record and localize sounds. This all relates to operating modes, so SonarPoint can be operated in various operating modes. Have a look back at SonarPoint configuration, the tutorial video on that, and you will see that there are several operating modes. Operating mode number 1, standalone, is not for sound source localization. So we will concentrate on the other ones here, and I will call them out. Let's start with deployment of a submerged array of recorders without surface expression, so nothing at the surface, and with optional acoustic synchronization, or if it's short term, then just using the internal GPS to set and calibrate the clock without further synchronization needed. In this first case, without acoustic pinger synchronization, you are looking at a clock drift that translates to a position drift of about 8 meters per 24-hour interval. So here you see 4 recorders rigged for a subsurface array with recovery by acoustic release. Here are the 4 model ARC1 acoustic releases, and you will see their operation in a video a little bit later. And we are using hard floats. They are quite inexpensive, $15 or so. You can get them online with a depth rating of several hundred meters. These are 8-inch diameter hard floats, and here you have 4 of the small recorders, the SP300-2. So that would be for a short duration deployment, probably days into a couple of weeks or so. Now, as you are getting ready to deploy your submerged array, you want to set and calibrate the clocks. That happens after you switch the recorders on, and we discussed that in a prior video as well. And so here Tyler is now making sure that they're all synchronized as indicated by LEDs blinking synchronously. On the 4 recorders, we also see an SPP synchronization, acoustic synchronization pinger here. What do you use for an anchor? In this case, we are using Sandbags, with the bag being a biodegradable material. So after some period of time, it will degrade and only a pile of sand will be left on the seafloor. And in this picture, you can see the sandbag being connected to this ARC here. All right, just for scale reference, we are operating here out of an 18-foot rigid bottom inflatable. For a lot of these deployments, that is sufficient. Of course, within your reasonable distance from shore, good access with your smaller vessel here. Notice also how Tyler is holding a rope here in his hand. That is to gradually lower the mooring string below the surface. Take a look at it here. He's holding his hand in the water. You see the rope here going down to the sandbag at the very bottom, looping through, coming back up, and he has now gently lowered the array until the acoustic release, the recorder, and the buoy are submerged, and then he will let one side of the rope go. The rope will pull through down here, and the string will submerge. Why this careful operation? That is to avoid shock loading on the ARC if you were to hold everything in the air, supported maybe rather than having it lowered on this rope here. If you were to hold onto the hard float and then lower it over the side of your boat, you might put a shock load on the ARC, a sudden spike of load, and you might break the fuse wire on the ARC. So this is a more gentle way of going about it. And here in this next picture, we now captured our mooring string, as you can see, rapidly descending to the seafloor. In this particular case, there's a 5-pound lead weight at the end of it, or possibly a 10-pound lead weight. Not quite sure on that anymore. Here you now see a mooring string sitting on the seafloor. So we just, scuba dive down to it. In this case here, look at the weight here. This is actually a steel weight, just from, gym weights for a weight bar. And this one, I believe we used 25 pounds of weight here. And here you see the recorder, the acoustic release, and in this case here, the synchronization pinger to keep this array self-synchronized to itself for a longer deployment of a few weeks. Another picture of a mooring string, this time without the synchronization pinger. So the length of your anchor line here is adjusted to where you get your recorder to be a reasonable distance off the seafloor for good acoustic reception. But be aware, if you have strong currents and surge, the longer your anchor line is, the greater the arc that the recorder will describe as it's getting pushed one way or the other in the current, and therefore the lesser the position accuracy or sound localization accuracy that is available to you. Here we have now triggered the acoustic release, and the mooring string rises quite rapidly to the surface, leaving behind the sacrificial weight or sacrificial anchor on the sea floor. Going back to the picture of our sacrificial weight or anchor here, there are areas where you will not be allowed to leave anything behind on the seafloor. In particular, in marine sanctuaries, we are encountering that at Desert Star right now, as we are deploying recorders in the Monterey Bay National Marine Sanctuary. And one option for you is to not rig your ARC to leave behind the sacrificial weight or anchor, but rather to pop a buoy to the surface and then haul in your whole mooring, including whatever anchor you use, from that buoy line. That's a technique that is used in the fishing industry for lobster and crab, groundfish, where having permanent buoy lines in the water column is becoming problematic now due to whale entanglement risk. But there's also other reasons why they do it. If you have a static buoy at the surface, obviously it's quite at some risk of a boat running over it or vandalism, poaching, and so on and so forth. So how would you do the rigging to achieve this? So here we are seeing a rope bag, as is used by the Dungeness crab fishery in California. And you can see a length of rope in this mesh bag. This here is the bottom end of the rope leading to the anchor. And then the top end of the rope has these buoys connected to it. The bag is closed here, and this release cord is rigged like so with this bungee cord here. Once the ARC triggers, its lever opens here. The release cord pulls through the ring, opens the bag, is pulled down by the bungee cord, and of course by the flotation force of these floats that want to come out. And now the floats can pop to the surface. Let's have a look at a excerpt of a BBC video showing this kind of operation in action here.
What the idea of this ropeless fishing system is to eliminate all of this, which is where boats and whales and other things get entangled, and to just store everything at depth, right alongside the creels.
The idea of this is that the rope sits in a bag or a container on the seabed next to the last creel, and then when you press a button, you activate a transponder, this device here, and it releases the buoys, and the buoys bring the rope up to the surface. So the real difference is that the rope isn't in the water column the whole time, and that means for animals like basking sharks or whales or the likes, there's almost no chance of entanglement because there's no rope there to get entangled into.
For the fishermen and for us, it's important to see the technology in action. A stormy day won't stop this, and the creel and the bag are chucked over the side.
3, 2, 1.
When the pots are ready to be harvested, an acoustic signal is sent to the bag from the boat, releasing the buoys, and they rush to the surface.
So there you saw the video. Of course, rather than having a trap at the end of your anchor line, you would have an anchor that is going to get pulled up as you are hauling in the whole mooring string starting at the buoy end. And you would probably have clipped the recorder itself somewhere to the anchor line so that this bag floats above your recorder. So that's a way of making sure you leave nothing behind, but be aware of the additional risk of developing a snag here as the buoys are trying to pop up to the surface. If that were to happen, you should be prepared for an alternate recovery plan, whether that is grappling, whether that's use of an ROV or similar. So that's the trade-off we are looking at here. Let's move on now to a different deployment mode. This is Ocean Drifter, and that would be SonarPoint operating mode number 3. So an Ocean Drifter array. An Ocean Drifter array consists of several of these floating recorder moorings or drifting, and the elements of it are, and then you have a recorder and then a cable connecting the recorder to a surface buoy. Here's just a foam buoy with a PVC pipe going through it, a weight at the bottom of the PVC pipe so that the buoy will stay mostly upright. Then here you have a unit called the RPT1, repeater 1. What this contains is a GPS receiver so that the recorder can be time synchronized and stay time synchronized. So the GPS 1 PPS timing signal is sent down the cable to the recorder. And then there is also a radio modem integrated in the RPT1. And the radio antenna is at the top of the pole. Flag is tied to the pole to make it more easily visible. And so there's radio communication back to your boat from the drift array, including the current position of each buoy. So as you're out there rapidly deploying these drifter buoys, maybe around a school of migrating killer whales, is a thing that we did, or some other animals, then you can still get a radio message as to where it's located at any time, so you can recover it again. Here you see a close-up of the buoy, the surface portion of it, floating here on the surface. Notice there's also a solar panel connected to it. So the rechargeable battery in here is solar charged for long endurance. It charges during the day, and then at night it can use that charge, or when it's cloudy and so on. And then you see the cable coming out of the repeater, providing power and data exchange and synchronization to the recorder somewhere below here. How does this work out in a small boat? Here we are again on our 18-foot rib boat, and you can see we have 1, 2, 3, 4 of these buoys in our boat, and there's still enough place for a crew of 2 or 3 people in the boat. Now here is a drifter array deployed around Monterey Bay, and you see 2 of these buoys here. They're actually quite a ways apart. This is taken with a telephoto lens, which kind of compresses the distance. And here you see some humpback whales swimming past. Okay, as I said earlier, we tested this out with killer whales as well as those humpback whales in Monterey Bay. Killer whales were over in the San Juan Islands in Washington State, at the border with Canada there. And here's just a quick look at some tracks obtained with it. Here you can see the tracks of several animals, so the sounds were localized, and you can see that the animals are migrating here in this southwesterly or southerly direction, as you can see here. So it's a part of killer whales all going in the same direction. And variation on this mode is similar buoy strings, but now equipped with an anchor and sitting on the seafloor. And so this would be now a moored array with surface buoys. And what is the advantage of the surface buoys? Well, the advantage of the surface buoys, for one thing, is solar power. So if you're monitoring for an extended duration, maybe you will use surface buoys. I think they will probably be more heavy duty than what we used here, but that way you could keep a recorder running for a very long time, a recording array, only every once in a while exchanging memory on the recorder, and a recorder can have up to 8 terabytes of memory. So the 8 terabytes would be enough for 15 months of recording at a sample rate of 100 kilohertz, 100,000 samples per second. So now you could have a moored sound detection and localization array with an endurance between servicing to recover the memory cards and replace them of over 1 year. Here's a look at a surface buoy part of a moored array close to shore here. This one further away. The other one was over here on the left side of this dam. Let's take a look at some of the sound localization we obtained. Here's a layout of our moored array with the surface buoys. These are the 4 recorders here, and their spacing is give or take 500 meters. Notice this scale bar, this is 171 meters. We then drove our 18-foot rib boat in a slow circle, and we recorded its position track with GPS. And suspended underneath the boat was an underwater speaker through which we projected several animal sounds and other types of sounds, like echolocation, clicks here, the C. The P is just a ping signal from an acoustic pinger. A is a human announcement. B is a buoying. It's a type of a sound that killer whales make. And S was some sort of another whale sound that we recorded here, killer whale sound, I believe. Not quite sure anymore. But you can see how closely these localized positions match the boat track. Let's zoom in a little bit, and they still match very closely. You see some of them indicate a residual error, so the accuracy of the fix can actually be estimated just from the localization process itself. This one good to within 1 meter estimated, within 6 meters, within 3 meters, within 2 meters. Some of them don't have that information. You just see an NA here. That means the sound wasn't received by 4 recorders, but only by 3, and so we cannot estimate the accuracy of the sound localization here. Moving on to our final deployment configuration example. Now we have a cluster of wire synchronized recorders. What is this? You have now 4 recorders mounted on this frame. Each recorder has a cabled hydrophone connected to it. That hydrophone, all these hydrophone cables go up here to this hydrophone cage where we have a small 15 centimeter baseline tetrahedral array. On the other end of the recorder, there's a synchronization harness. Here, sync signal and data can be exchanged. And now one of these recorders is configured as the master recorder, which is operating mode 4 or 5, and all the other ones are slave recorders. And so the master recorder will instruct the slave recorders when to record. It will send a command through an RS-485 data path saying, hey, start recording, and this is the date and time stamp for your recording, and it'll be a 10-minute recording or whatever it might be. Then the master recorder will send its sample clock, and the slave recorders will use the sample clock. So we have sample clock propagation that provides excellent synchronization accuracy. Well into the subsample region, it's accurate to within about 100 nanoseconds, that is a tenth of a microsecond, whereas one sample interval is if you're operating at 400 kilohertz, then it would be 2.5 microseconds. So you're well in the subsample region here. Why would you use this kind of operating mode? Well, one reason is that it allows you to really keep your localization array out of the water column. So this heavy frame just sits on the seafloor. You don't have any mooring strings, any buoys, or anything in the water column. And I should say each one of these frames will provide you a 3D bearing that is azimuth and elevation to the sound source, like over here, for example, if it was submerged. And then you will need to have at least 2 of these clusters, 2 frames placed in different places, and that the intersection of these 2 vectors, one from each frame, would localize the sound. Let's take a look at the tetrahedral hydrophone array. These hydrophones are from manufacturer HTI. I believe HTI-99-UHF. So they handle the whole frequency range of SonarPoint up to 416 kilohertz. And you can see that they are in a defined spacing, about 15 centimeters, which is about 100 microsecond signal runtime. Imagine now sound came from over here, roughly, which hydrophone would receive it first? This one here, and then sometime later, maybe a little bit less than 100 microseconds later, this one, and of course this one up here. And based on that, you could say, well, this guy received it first, so the sound came from somewhere over here. You can compute it precisely, get your 3D vector there to the sound source. One application for it, and the reason why this was developed, is to localize sounds from dolphins and porpoises around this underwater tidal turbine made by Minesto, and this here is in the Irish Sea. So this turbine is tethered to a mooring point on the seafloor, and it flies like a figure 8 underwater, thereby experiencing a faster apparent current than the real tidal current is, making the turbine more efficient. Let's look at this diagram here, and here you can see the base to which it's tethered, and during ebb tide the turbine might be doing a figure 8 here or flying over in this direction, and then during flood tide the current now goes the other direction. Then the whole situation reverses and now your turbine is here. You can see if you had mooring strings somewhere in here, they might interfere with the tethers, mooring strings for, you know, a localization array. So if you have just this frame sitting on the seafloor, very low profile, you don't have a problem. And the point then is to localize sounds, vocalizations of dolphins and porpoises. Maybe this is indicative of a porpoise or a dolphin coming this way, might be colliding with this kite, this one turning away. So that's the general concept here. Here's a look at the data output. That one is generated here by Gemma Veneruso of the University of Bangor for Minesto. You see these very slow dots. They're just noise clicks. I should say in this graph here, X is the time axis and Y is the bearing axis, where we here have 0 degrees up to minus 180 and up to plus 180 degrees. And a few click trains from dolphins or porpoises, these are residual dolphins, it says here, are highlighted in color. Here, this gray one here, we have it at 110 degrees or so. And in this graph, here X is the time axis and Y is the bearing axis, where we here have 0 degrees up to minus 180 and up to plus 180 degrees. And a few click trains from dolphins or porpoises, these are residual dolphins, it says here, are highlighted in color. Here, this gray one here, we have it at 110 degrees or so. And in another direction, the orange one, the green one, there's a purple one down here as well. So you can see you get these vectors to these sound sources, and if you now have 2 vectors from 2 of these frames, wherever they intersect would be the location of the animal.